Hi, everybody. So I hope that you're finding this week okay. I know that there hasn't been as much work as past weeks. Like I had indicated in the work outline, I think that a lot of people are feeling overwhelmed, maybe fatigued. It's week 6 of this remote learning process. And I think that we just all need to make sure that we are taking care of ourselves and not getting overwhelmed with the work that we have. Because even though we're asking you maybe to spend less time per subject on work, I think that you guys have a lot going on in your life. So take a step back this week, take care of yourselves, check in, let me know how you're doing. Focus on that weekly assignment, which is really just a check in. Let me know what one thing you're doing to kind of help with coping or mental health. It could be going for a walk, doing gardening, playing a game, reading a book. Let me know what it is and just check in with me. I want to make sure that you guys are okay. So I thought I would just quickly make this video to take up the homework from last week. We were talking about sources of light, and there's a few different sources that you were to fill in the chart with. So the first one is radiant light, and this has to do more with chemistry. So if you guys remember those hydrogen atoms, they have one electron on the outside, and they are actually able to fuse together. And as soon as they fuse together, they become helium. And so you have four hydrogen atoms like this, these protons, they fuse together and they become a helium molecule. And that helium molecule, as soon as that fusion happens, these come together, these protons come together with the neutrons from other atoms, and they release all of this abundance of energy. So the energy is basically excited electrons in the gas on the outer layer of the sun. And this is what we see there. This is that radiant energy. And when these electrons return to their ground state, so when they return back to normal, light is reached. Okay, so they get super, super, super excited. They give off all of that energy. They come back down. That releases all of light. The next source of light that we have is incandescence, and this is used in most homes. Light is emitted from an object when it's heated at high, high temperatures. So this would be if you have coil lights that look like a swirl. Those are not incandescent light bulbs. This would be more of that traditional round light bulb type that has this coil on the inside. That coil heats up, and when that coil burns out, the light no longer is there because the electrons are not able, the electricity is not able to flow from one end of the rod to the other. Okay. As you heat up, you actually have this progression of color. So you're going to start off with red, orange, yellow, white, and then you get this bluish white. So that's also why as you turn them on, more heat is emitted. You're going to see that the color does in fact change. It gets more bright in the room. Okay. This is how much energy is given off by each of the lights. So you guys can pause this and just read through the table here. So this side are light bulbs, and then this side is just kind of a reference for, like, for instance, a candlelight is going to give off 2000 Kelvin, and so on and so forth. Okay. So again, that's just energy units. So examples: a burning candle is actually going to cause the spark is caused by friction, which is kind of the same thing inside of an incandescent light bulb. Electric discharge. So we see light as well during a lightning storm. Light is produced by passing an electric current through gas. So this is what happens during a lightning storm. The electricity causes the gas to glow by exciting its electrons. And we see this as electricity passes through air. You also see this in these neon signs. So neon actually helps to promote these signs. So they get excited, they're passing through that air. And we talked about this in chemistry as well. The next one is phosphorescence. So this is really cool. You guys may have had these when you were growing up. You might still have them. So those glow-in-the-dark stars. And objects are coated in this substance, and it's called phosphor. Phosphor has this unique ability to absorb light energy, and usually it's UV light. That's the light that works the best. It does not release that light immediately. So that's why you need to charge these up, right? So you guys could remember that maybe all day or before you go to bed, you put those lights on for an hour, and then as soon as you turn them off, now you have this glow in the dark product. And then over time, that light dissipates. So it goes down, okay, over a long period of time, which is why when you wake up in the morning, the next day, the stars are no longer glowing in the dark. Fluorescence. So this is really similar to phosphorescence, but light now is immediately released as soon as it's absorbed. So there's no time delay. And UV light is absorbed and released as visible light. So we see this like highlighter markers appear to glow because they are constantly absorbing UV light, and it releases it as a visible light. This also happens with blood, urine, and semen, and we can see that these are detectable at a crime scene, and you can use this UV light because they're fluorescent. So we actually spray them with a compound that helps to make that fluorescence a little bit more pronounced. But this is exactly how it looks. So on this carpet here, you can't see anything to the visible eye. You apply the light treatment, turn it off, and now you can see all of the specimen. And we also have this in fluorescent light bulbs, which are those long cylinder tubes, which give off very, very bright light. Chemiluminescence. So now light is going to be produced as a result of a chemical reaction. There's not going to be any heat or very little heat is produced. A great example of this is glow sticks. So the chemicals are initially separated inside of the tube, and you have to crack that tube. So you guys probably have done this, right? So you buy the glow stick. I usually get them from the dollar store. If we were in class right now, I would do a demonstration. So you buy them from the dollar store and you take them out of the package. They are not glowing. You crack them. That kind of makes them, doesn't kind of, it actually does. It makes the chemicals combine as soon as that seal is broken. And as soon as those chemicals combine, now they're going to glow. And again, this dissipates over time. So it becomes less bright over time. This is useful in times when light is needed, but sparks could be dangerous. Okay, so these are flammable, so you need to be very careful. Bioluminescence. So now this is nature's glow in the dark. Light is produced by living organisms. So we see this in jellyfish. You can see this in fireflies. Those are really good bioluminescence. Basically, what's happening is it's the same idea as a glow stick. That chemical reaction is occurring. Very little or no heat is being produced because you don't want to kill yourself because light is being given off. Right, so you don't want to kill the animal that's giving off this light, or it doesn't want to kill itself. That's why no heat is given off, but this is used to kind of ward off predators. So predators don't really want to eat something that's glowing that looks like it could be toxic. Triboluminescence. So light is produced from friction, such as scratching, crushing, or rubbing of certain crystals. So, for example, if you have sugar cubes, you can create light if they're brushed quickly together, or if you were to shoot a bullet through one. So I'm going to post this YouTube link if you want to watch it. But yeah, so something as simple as a sugar cube that can produce that light there. Light from a light emitting diode, so an LED. Most of our TVs are made from LEDs. So basically, what happens here is an electric current is going to run through a diode, and a diode just looks like this right here. So it runs through the diode constructed with a semiconductor. So remember, a semiconductor is any material that allows a current to flow only in one direction. So if it was a full conductor, then now the current can flow both ways. But because it's a semiconductor, that current is only going to flow in one direction, like you were going down a one-way street. When the current passes through the LED, it's going to glow without producing any heat. So this is the diode right here. So you're going to apply that current. It's going to light up through that LED chip right here, and you're not going to have very much heat. So over a long period of time, like TVs could light up, but I mean, like you think about how long your TV runs, and it's not going to get super, super hot because you don't want it to melt, right? That would be a very, very, very bad situation there. You also see some of these examples. So the small red on buttons on computers, those are the same idea, as well as some Christmas lights, those tiny little Christmas lights. And then we also have lasers. So lasers is actually an acronym for light amplification by stimulated emissions of radiation. Basically, what happens here is that you're going to emit light in a single aligned wavelength of light. So right here, if this was a light bulb, you see how all of these, because it's a white light, so all of my different wavelengths are flowing through here. If this is green, now they're all flowing green. It's that one wavelength like this, but they're not all in one direct path. It's not super direct. Think about if you were to shining a light, that light is dispersing throughout a whole space. It's not pointing on one little thing. But in this laser now, all of that light is super concentrated, so it's going to cause that one little dot there. Okay. What happens here is that that very visible light is going to be super pure. So light is going to be incredibly intense because of electromagnetic waves, which we talked about last week, and they're all traveling in one direction and at the same time. Basically, we can use lasers for various different things. So we can use less intense lasers in a presentation or to draw someone's attention to something. You can use them to burn very precise holes or cut objects with very precise or oh my goodness, with precision. Basically, what happens here is high frequency lasers are only visible beyond the visible spectrum of light. Okay, so that's what happens here. We actually can't see high frequency lasers, so they can cause damage. And you can also use lasers to measure for distance with accuracy because of that concentration of beam. So we have large lasers that can actually measure the distance between the moon and the Earth. Okay, and again, I'm going to post that YouTube video. That's it for this video today. Next week, we're going to talk about the ray model of light. So be prepared to learn next week. There's not going to be any more work periods. Take this week just to kind of hang out, get caught up, email me questions if you have them, and don't forget to submit that assignment. Miss you all.